Okay, so today we have the 10th lecture by Harvey Friedman of 2025. It's the eighth part of invariant maximality, please.
Thank you. Okay, so today, so to review, the text of the previous lecture is at the downloadable lecture notes page. Um, and it was on section 4.4 of the reversal. Also, the current version of section 4.4 in full is on my downloadable manuscripts page. This is the pattern I've been following uh, in the rollout of this reversal. And I orient ourselves in the beginning a bit here. So we are reversing this statement, which is unchanged. OI means order invariant. Order invariant maximality, clique, and this is the name of the function that the invariance is for. Every order invariant graph has a blah invariant maximal clique. Um, the positive part of all this is going to be updated in lectures after we finish the lectures on the reversal, after we finish the reversal. And it includes streamlined forms of this and how what else can you put in here other than this? What if you don't what if you have a simpler thing like you don't have the parameters in here, blah blah blah. All that stuff is uh, going to be lectured on in its most modern form, up-to-date form in after we finish the reversal lectures. I'm expecting two more reversal lectures after this, two more only. And we can talk maybe at the end of this a little bit more about that. Okay, so um, review. This is unchanged. This is the table of contents of the reversal. And we've done 11, 10, 9, 8, 7, 5, 4, uh, and now we're at 3. And 6 is a bookkeeping section um, designed to document that we haven't screwed up on the definition of the order invariant graph. More about this now in a moment. Meaning, yeah. So today we discussed 4.3. And it's 4.3 that the reversal starts in earnest. 4.1 and 4.2 is infrastructure stuff. Infrastructure stuff set up for the setup to prepare us to begin the reversal. So this is really the beginning of the reversal is the section we're talking about today. Now we got to talk a little bit about what leads up to section 4.3. Otherwise, it won't make good enough sense. So we have only the preliminary sections, as I said, 4.1, 4.2, and the reversal starts in 4.3. Uh, in section 4.1, we start with the statement we're reversing. This is unchanged. And we fix an arbitrary number k large. Uh, square brackets 3 means there's three twos, three exponential twos, 2 to the 2 to the 2, with 1,000 on top. This is just to be, nobody worries that this is big enough for things we do, uh, and it's convenient. So it really is not, has no significance. We move to proposition A. So this is just this recast with a different notation. Every order invariant graph on Q minus 1, 1. Oh, yeah. Proposition A is just this statement for the K. Using the K. So we use the exponent K12 has a J invariant maximal clique. Okay, two things here. We're going to make the exponential even bigger, K12, than this arbitrary number K that was picked. We're going to make this even bigger, and this is K. This is 12 twos with a K on top. Um, and this has a J invariant maximal cleave, where J is the function we've been talking about here. This maps, this is the identity on the negatives, is the identity on the negatives here. And it just shifts by one divided 1 over K12 in the serious part here. Okay. That's the same thing as this function here. The same thing as what this is. It's just with K12. That's, just better notation, more usable notation in the text to use J. All right. So, um, okay, we define the languages L of R. These languages are the totally standard ones, uh, almost totally standard ones of ordinary predicate calculus with equality, with a binary relation less than and the R area relation RR. And we use these logical operations to simplify things. Uh, and here we have, full closure under the logical operations. And we don't use equality. It turns out that when we do stuff, equality will be obviously defined, in the structures we're talking about. So there's no reason to put equality in. Now, importantly, we define three unusual languages, though. Three unusual languages with only finely many formulas each. This is important. Because we can't really do much with this big language, this full language. We're after all, we're starting with very little. We're starting with a statement we're reversing. So we define these language fragments L of NMR, language fragments L of NMR. And this consists of formulas of logical complexity at most n. Yeah, these languages are part of uh, this is a fragment. I should say this of L of R. This consists of formulas of logical complexity at most n in a standard way of doing logical complexity with m variables, only m variables, v1 through vm actually for specificity, and the binary relation symbol less than and the RA relation RR. And if we put a naught down here, that means it's the quantifier-free fragment. Now, it turns out that almost entirely we're just going to use three particular fragments. We shall see right here. Here we are. These fragments are L of K1, K1K, and L of L naught of K5, K5, K4, and L of naught of K9, K9, K8. That's why we use dimension. We use K12 as the dimension and the length of the indiscernibles, as you can see. The number of indiscernibles actually is these reciprocals, no fractions with denominator K12, and they're K12 plus one of those, right? Because you start with 0. Go to 1. That's why we went up to K12 because we want to conveniently have these smaller numbers, but they're still very big and they jump very high. So that's why I use this kind of thing, K12. It's only late in the reversal, section 4.7, which we already did because we're working backwards in the lectures on the reversal, that we get to use the ordinary L of R because you need to build up a lot of machinery to be able to handle the full language. All right, so we enumerate the formulas of the languages we just described. And the enumerations are without repetition in an orderly fashion, i.e., a formula only appears after its constituents appear. It's just sort of the obvious way you would want to do enumeration. And I'm very specific about it in the text. I just don't wave my hand and say do it sanely. I actually give it explicitly. All right. So for the semantics, the structures are always very special for the semantics for these three languages. And yeah, namely that the domain is the domain that we're using throughout the reversal until that we use originally for the reversal. Eventually we moved to structures with different domains. Most notably, you might remember we played around with, for example, Q of 0 to infinity, uh, with the left endpoint 0, but not that's much later. That's not the very early section. All right, so Q minus 1, 1 less than, and the relation where R is either K or K4 or K9 as, I'm sorry, K8. Yeah, got to keep this straight. Yeah, respectively. And assignments are finite as they assign only to the variables. There are only finitely many variables. So assignments are of exactly the same length as the number of variables, V1 through V V1 through VK1, V1 through VK5, V1 through VK9. And now only the first language uses uses only the first language here uses quantifiers. The rest of them, and the quantifiers are always bounded. So we're always going to be writing sat with a less than q in the exponent, meaning that the quantifiers range over the numbers below q. They range over here. And it's important that these quantifiers be bounded. And Q will actually turn out to always be negative. The negative numbers are where the safety is in this statement. That's why we had the last section we talked about, which is section 4. Section 4.4 was called negative reduction. It's the negative numbers that we have we can do a lot with. We can't do as much with the uh, non-negative with the positive numbers. Uh, Although we do a lot with the indiscernibles, uh, the I over K12, but the numbers in between uh, are difficult to deal with. So if you remember, we went into the negative part. All right, the assignments are not required to be. This is just for officially. All right, officially. The assignments are not required to be less than Q valued. However, when we actually apply the semantics with this, we will be requiring that max of X uh, be less than Q. Yes, 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 yes. Okay, now in section 4.2, now we're not talking about 4.2 today, we're talking about 4.3, but I have to give you some background. In section 4.2, we set up a bunch of infrastructure for defining the all-important order invariant graph G that we use in proposition A. So this graph is complicated, um, and we have to be careful that we don't have the reader be abused by defining the graph in front of it before we use it. I mean, it would just be pages and pages of totally uh, non-motivated clauses. So we need an infrastructure to talk about what's going on. And I'll say more about this in a second here. So with this graph, an order invariant graph, that means order invariant graph means just a graph. Graphs don't have graphs are what's called simple graphs. Um, uh, they are undirected and there are no loops, no loops. Yeah, simple as possible thing, right? Um, and order invariant means um, edge relation or the adjacency relation is an order invariant relation of twice the dimension. Right. Okay. So I think we said that maybe 80 times during all these lectures, but yep, we just remind you of that. All right. With G, we let S be an arbitrary maximal clique. That's how this argument is structured. And we have to show that because of G, a maximal clique in G is a very powerful animal that allows us to spin off a model of large cardinals after many lectures, right? Actually, the lectures went backwards, of course. Uh, so G has to be a pretty hefty kind of complicated graph in order to pull this off. Uh, and we use G very much. I mean, it's heavily used in section 4.3 that we're talking about today. Uh, and uh, it's relatively light direct use in sections 4.4 and 4.5. Sections we already did. In fact, you might not even remember G being all that explicitly mentioned there, although it's in the background, so to speak. All right. I mean, much more in 4.4.4.5 is just facts, is just arguing with S, the maximal clique. And we know a lot about S from section 4.3, this section, at the end of section 4.3. The maximal clique S is heavily used. Yeah, as I said, yeah. Now, in 4.7 through 4.11, we're way beyond using the graph. We're way beyond using even S. We've already morphed into structures which are thought of on their own, structures on their own, without reference to graphs and cliques or anything in 4.7 through 4.11. 4.6 is this bookkeeping section I mention all the time, which is needed to track that the properties of G are in fact coherent. So I use various facts about G without actually defining G fully. And G is essentially defined fully in section 6, but we have to make sure that I haven't uh, that I've kept things well defined, that there's no interference between the different things I use, though they don't conflict with each other, so to speak. Okay, now G is far too complicated to simply give its definition, as I said. So we roll out properties of G when we need them to verify a claim about G and the arbitrarily chosen maximal clique that's invariant. Sorry, that's invariant. Uh, no, with G, we let S be an arbitrary maximal clique, an arbitrary J invariant maximal clique. This is very, very wrong what I wrote. Sorry. J invariant maximal clique. All right. So section 4.2 is setting up the infrastructure for treating the order invariant graph. Um, and uh, we will postpone talking about this detailed infrastructure until the next lecture. Although I will talk about blockers. Yeah, talk a little bit about talk a little about blockers. So this section is called atomic representation. And okay, this is review of what things I said already. We will use this yeah, we will use all assignments. Well, no, there's something new here. We use all assignments of length K1 for this language. We will be using them, but also it's not really quite right. All assignment. All right. We use unrestricted assignments. I don't know. Yeah, let's say that. However, for these bigger languages, although they're not really bigger because we only take the quantifier for each part. Otherwise, they would be bigger. All right. We will only use certain assignments of length K5, K9, respectively. Only certain assignments are really going to be used, and it's kind of useful to know what I'm talking about. D is this domain. I use D for the domain of the function J. Um, Um, yeah, the function J. Our invariance of the thing we're invariant with respect to. And the range of D is D without zero together with one. We have to use one. And it's J of P equals P if P is negative and P plus this otherwise. This is review, that's nothing new. Um, and D is really the domain of J. All right, now it's V and W that I use for these other languages. They're very specific. We only want to use stuff in D. See, we only want to use stuff in D for the assignments um, of length K5, uh, and we also don't want it to get too big for technical reasons. So less than or equal to a half, and um, and W is also less than or equal to a half. And these are like K9 instead. Um, and we need a double max for technical reasons is the same as the max, except that we max with zero. We make sure it's non-negative. Uh, just notation for what I'm going to show you. Yeah, we use V and W for our assignments uh, with these two languages. By the way, these two languages are not important, except for the fact that we need them in order to prove stuff about the really important language, which is the LK1, K1, K. These are auxiliary languages needed to carry out arguments. By the way, you saw that, when we did section 4 last time, since we're going backwards. All right. Now, we start with handling what amounts to a negation case in our development, a negation case. But actually, the way we handle this is extremely indicative of how the whole section fits together, how this whole section runs. It's a very nice combination of using the invariance, using the maximal clique and the invariance together. Each one alone can't do much. It's the combined effect of maximal clique and invariance. Well, of course, that's not surprising because the statement is nothing but a combination of those two things, right? But you can see how I'm combining the two when I just handle this statement, which is sort of like a negation case. You see here. Uh, that S holds um, yeah, that S holds at the kind of tuples we're looking at. These are the only kind of tuples we're really interested in this section. These tuples. I mean, we're interested in these, right? But under S, we are interested in this stuff where we use the indiscernibles, because these are going to be the atomic representations. So this whole thing here says that two atomic things are equivalent, namely that, and notice that the second one is smaller than the first. You see, the second one is lesser than the first. Now, by the way, you can put it turns out this is the right way to do this. This is the most convenient way to state this for what we want to do. But actually, you could think of it also as negation reduction, because this could be a not here. The not could be here, and the not and no not here, right? We all know that A if and only if B is the same as not A if and only if not B, right? So, or A if and only if not B is the same as not A if and only if B, right? So we can think of this as kind of a negation reduction, if you like, but it's done it's done the other direction. Uh, for technical reasons, this is better. All right, so this is the same thing, except that it's for the other languages. For the other languages, the same thing. But we want to start with max y here. We want to start with something beyond y. And we don't want, when y is purely negative, we don't want to start with something negative here, that it wouldn't be indiscernibles. A negative number plus 1 over k 12 isn't necessarily an indiscernible. So that's why we use a double max, MAXX, to make sure this is at worst 0. The smallest it could be is 0. Yeah. Now, you should know, I'm going to note this again. I'll just say it first time. There's a no interference between all these three, because X is not too long, right? X is not too long before things really start to go. Just one more term, and then things start to go into the indiscernibles. And Y is bigger, much bigger length K5, actually K5, before we start to get into this, and Y is negative. Not negative, but the point is it's a long time before we start this, and this is even longer before we start this. This is something here. This is not right. Yeah. So um, you can see how I'm making sure that this is set up so I don't get interference. This is important. All right. Now we're going to use the fact that X is a maximal clique. Actually, S is a maximal clique. It can be written in many different ways. One is a vertex lies in S if and only if all vertices other than itself are adjacent to X. This is one way to say you have a maximal clique. Another way to write it is S is equal to this, which is just a translation of one. S is a set of all X such that for every Y in S without X, Y and X are adjacent. Now, I want you to note, I don't want to go further because I want to keep this up here for a second, but you should note that 2 is a kind of comprehension axiom, isn't it? See, being a maximal clique is a kind of comprehension for S. I know it sounds a little strange, but that's um, oh, I just talk about why this is true. This is just a triviality, um, important triviality. Note that 2 can be viewed as a weak form of comprehension. In fact, it's a single special case of parameterless comprehension, right? By the way, this eventually becomes high-powered comprehension in large cardinals, you see. But there it starts. There's the comprehension. It just starts right here. You see. All right. Now let's look at this A above. The construction of G has to be based on, so now I say a little bit about how we do the infrastructure. The construction of G has to be based on blockers of vertices, where blocking is half the story of non-adjacency. See, non-adjacency can happen with one vertex being non-adjacent to a lower one, and one vertex being non-adjacent to a higher one, because the vertex can have two roles, right? One is it's a high guy, and the other is it's a low guy, right? Because there's always if it's because it always there's something bigger, except at the top, of course. So you organize this by defining the graph is actually defined by the blocking relation, and the blocking is half the story of non-adjacency. So we have X blocks Y implies we're going to have that blocking is you only block higher things. X blocks Y implies max X less than or equal to max Y and X not Y. And define X and Y adjacent if and only if X does not block Y and Y does not block X and X is not Y. That's how that's the basics of how we roll out G, the blocking relation. And then the blocking relation, which is ordered variant, the blocking relation gives you the adjacency relation. But there are always two halves. This is always an issue. You can a vertex can have blockers and can block other vertices. Important. Now, one of the conditions that's important here is that if X blocks Y and X and Y are not both exceptional, exceptional is a technical term for we need to reserve certain we have to exempt certain tuples for this. So if X blocks Y and X and Y are not both exceptional, then max X is less than max Y. And everything we do in this section, everything we do explicitly is not exceptional. This is all non. We're going to do non-exceptional stuff. Okay. So basically, if you block somebody, you got to be lower. But you could block somebody higher. You could block somebody higher, but you could only be blocked by lower things. All right. Tuples are all not exceptional. Okay. Exceptionals are important in section 3.5. Sorry, 4.5 here. In connection with tupling. So that's a whole other story. And we did tupling, we used exceptionals in there. Okay. All right. Now, this is a bad English way of talking about the things that are not adjacent. But there's a reason I want to make the analogies between things I do here, the connection between statements I'm going to make as clear as possible here. So the most direct idea to prove that this negation reduction thing that I was talking about, the most direct way would be the non-adjacencies of this thing are just one thing, namely this. That would be the way to do this, because then we would have this. We would automatically have S holds of this if and only if S does not hold of that. By the way, this is exactly what we're trying to do, right? If you go back up here, this is exactly here. Look at 1A. Yeah, A. This stuff is very similar. You don't worry about this. This is what we're trying to do, right? We're trying to arrange for this. So we write down things in this section. We write down things we want to be true, and then we say that G was defined, so it is true. And then we have to prove in a bookkeeping section that all this is legal. All right. So so the non-adjacencies of this is just this. For then we would have this. This is this is a boring, trivial proof that you get this if you have this, if the non-adjacencies. But you have to control all the non-adjacencies. So in other words, 3 immediately implies 4 with a trivial argument that looks terrifying but isn't. Okay. Now, there's a problem with this approach. There's a problem with this approach because 3 is unrealistic. It's you can't really control and don't want to control the non-adjacencies. You only want to control the blockers. You control the blockers. I mean, there may be a dual form of this paper, of this stuff, where I only control the reverse of blocking, was what blocks other what are the things that things block. But that's a dual form. That might be exactly the same. But it might not even quite work. There may be some technical bugs in doing that way. Well, the basic thing is who blocks a given vector? And it's going to be something smaller, except the exceptional case, it might be something with the same max, but it's going to be in this section always something with a smaller max. Okay, but this three asks for all the non-adjacencies, including the stuff that this blocks. And this, we're not going to get. Three is totally unrealistic. It's much too strong. So how are we going to get this four from something that doesn't talk about all the non-adjacencies? Well, this is what we do. And this is the extremely powerful method for the whole section 4.3. And it also spills over a little bit into 4.4 and 4.5. All right, so we have to liberally allow non-adjacency with both higher and lower max, not just lower max. So what is manageable is the much weaker form of three. The blockers are just this. The blockers. And these have lesser max. And how can you possibly get away with something weaker than weak like this that doesn't talk about the other talk about non-adjacency generally? This is good enough for the following reason. From 3 prime and the order invariance of G, we obviously get 3 star. The non-adjacencies of shifting up is just what you would expect by chopping off the last term. Wait a minute. Yeah, this is wrong here. All right, I apologize because this might have to be reduced by 1 also, yeah. Okay, yeah. Okay, you immediately get 3 star from 3 prime because everything's order invariant. I didn't change the order of anything. Right, right. Nothing, no order has changed. I just moved everything up. But notice I moved everything up so that the last term is 1. The number 1 is very important when you're working in the space -1, 1 closed. 1 is called the right endpoint. This is very important. It means you can't go higher. So we immediately get well, it's not because of that. Yeah, so I'm not really saying this right. We get the order invariance of this. No, I'm sorry. Yes. Okay. I'm sorry. This is 2 steps. From the order invariance, you get this with blockers. If I said blockers, the order invariance gives you this with blockers. From 3 prime in the order invariance, we get this with blockers this is better said this way, blockers instead of non-adjacencies. Adjacencies. And since we cannot have a greater max, we get it for non-adjacencies as written. Yeah, so it's 2 steps. But then we're back to the same situation with these higher numbers, and so we can conclude this, right? Right? We get our equivalence. Now this time I did write it -1, so I'm sorry that I can't tell whether this -1 should be there or not. I can't tell at the moment. All right. Let's not worry about that. All right. So we get this, right? But that's not quite what we want. We have to go back and take these down to back where they were down here, right? we have to go back here. So this is 1 and 2a. So the difference is 2a minus 1. And the difference between these is all right, let me not screw this up. This is probably a wrong number, something like 2. All right, but you get the idea. Okay, so we obtain what we want in the first place by taking this down by j. Now that's the trick that we use throughout this section. We control the blockers only, not the things that things block. But then we argue that when we do that, we control the blockers of the stretching out of the extension out to where the right endpoint is 1. Right? So we can move the whole problem upstairs. And then we know that the blockers are the same as the non-adjacencies, and we can work our magic of the reduction because it's a maximal clique from the maximal clique. And then we cut it back down using the order invariance. I mean, excuse me, using the J invariance. Cut back down. And the parameters, the things that remain here, are always negative, so we're all right. Okay, and that's all this section is nothing more than endless applications of that. But of course, you have to make sure that that the blockers are done right. The blockers are done right in order to handle the induction cases. So that's basically what's going on. And I won't give too many more details. All right, so let's look at this negation thing again. We only talked about A, but B and C are the same thing. It just looks different, but it's B and C are proved the same way. It's the same issue. You go up and back. You go up using invariance and the fact that it's 1, and you come back using J invariance. You go up using order equivalence. No J invariance. You go up using order equivalence all the way up to 1, and then you do your thing then you use a maximal clique, and then you come back down using J invariance. And that's what all this is about now. And now this is what we're aiming to prove in this section. This is actually what we're trying to prove. This is called atomic representation, the title of this section. SAT is equivalent to not, and SAT is equivalent to not, and SAT is equivalent to not. We actually want to, there's a positive form of this where SAT is equivalent to S without the not. The other thing without the not. And for the induction hypotheses to work, you want to have both going on. Now, what we proved in some detail we discussed, right? This thing that we discussed, which is negation reduction, so to speak, proves obviously that 1A, 1B, 1C are the same as 2A, are equivalent to 2A, 2B, 2C, right? Because this is equivalent to the right-hand side's match. The left-hand sides are copied. The right-hand sides match because of the previous equivalence. In other words, this is true if and only if, with a not S. If you add 1, you have to add 1 here. Okay. All right, so this is a very strong form of quantifier elimination, which is actually more than that. It's quantifier connective elimination. And you're eliminating quantifiers and connectives is very important. Now, you can't eliminate connectives in O minimality and semi-algebraic geometry and things like that. You only get quantifier elimination, but you can eliminate connectives and quantifiers. It's the whole point of set theory is in comprehension and separation is the elimination of is atomic representation. All right, so this makes sense. All right, and we have to do non-interference since we use 3 different languages, that the tuples don't interfere with each other in this argument, and that's because of the very wide disparity between the lengths of what's going on. All right. This just comes out of the blue. We need to know that S actually has somebody in it. How do you know? S might have it. All we know that if S is a maximal clique, all we know is that the cardinality of S is at least one. But okay, so this uses that there are no blockers of these diagonals. They're all order equivalent, these diagonals, right? So you just take one of them. And they're not exceptional by definition. Obviously, nothing. Yeah, we have to define what exceptional is. That's the next. The infrastructure stuff is the next lecture. But how do I know that that there are no blockers of this tuple? Just one of them can be used. Why? Because I said so. In other words, I arrange in the graph that there are no blockers. I just say no blockers. You see, that's what I'm doing when I roll the thing out, so to speak. Of course, I better not say in the next page that here are the blockers, right? So that's what section 6 is, a bookkeeping section to make sure that I shouldn't go to jail for committing mathematical crimes, right? Okay, so we start with a case. Okay, so this is an induction argument, and I'm just going to briefly go through it because we're running out of time anyways. You're probably bored with this already. So we start with the induction case, which is just the atomic formula case in the three languages. So what does that look like? Xi less than Xj if and only if not S of this. You just say the blockers of this. You say the blockers of this are just the ones where Xi is less than Xj. Or the negation of it. I always get confused. Anyways, you do that, and then you use this stretching and going down thing, right? So that you actually have this. In other words, you're really talking about non-adjacencies if you push the thing up to the top where the last interval is one. And it's the same thing for the other two languages. Then the other atomic formula looks like that. Remember, you don't have equality. The other atomic formula looks like that, and then you just down here you make sure that the blockers of this are just the ones where are just the tuples with of smaller max with this. And yeah, so that's probably not accurate what I just said. Is these tuples. These tuples, sorry, are these. Sorry, that's what I want to say. The blockers of this are just the things that look like that. Yeah, that's what you have to say. And then why does that work? Because I said so. That's part of the definition of the graph, and that other argument about stretching and going back down. I mean, going up and down is used again, and then it's the same thing for the other two languages. Okay, and then the negation case is actually redone, but it's really the same as what we did. The negation case. Well, actually, it's not completely redone because the negation case was a special case. This is a little bit more general. So what you need to do is say is that the blockers of this guy are just these. The chopping down, because B is bigger than J. Yeah, B is bigger than J because of this. Yeah, and why? Because I said so, and that as I'm making up the graph, I'm the boss of the graph, and so that's why that works. And then here is the same thing. It's just for the other two languages. Now, what about the disjunction case? Here we have to say that the blockers of this guy are the blockers of this guy and the blockers of this guy. The blockers of this guy are just the blockers of those and the blockers of those. Then you push this all the way up again, and you get the non-adjacencies of this guy or the non-adjacencies of this guy and the non-adjacency of this guy. And that means that you get the equivalence that we want. But upstairs, when we push the thing up to 1, with the last indiscernibles used as 1, and then we push it back down again by J, because J preserves S and not S, of course. Yeah. So then we do it for the same two languages. And then the existential quantifier case, it's the same idea. The blockers of this are just going to be these guys, and this time there may be a lot of them. Yeah, sorry, these guys, where now P can be anything, less than Q, sorry, less than Q, of course. Yeah. Before the number of blockers was basically 1 or 2, but here in the connected cases, and more in the atomic formula cases more, but it's more trivial. And here the number of blockers is quite high because of this. The changes. That's because this is an existential quantifier case. And why is this? Because I said so. I'm the boss of the graph. And yeah, and so that works with the same idea. You stretch up, everything's fine if the last term is 1, and then you pull back down by J, by the J invariance. There isn't any case 5, B, and C because the other languages don't have any quantifiers. So now we've established 3 things. The first one is that if you have an assignment and Q is negative, the quantifier limits are always negative in this paper, so to speak, in this section. This is atomic representation. SAT holds if and only if not S of this, if and only if S of that. And the first thing we did today, in detail, was that these are equivalent on their own, but we state it all in one fell swoop. We state it this way. Okay, so, and it's convenient to have both S and S, not S. Well, first of all, the induction steps need this. If you go into a detail, you need to do both, assume both at once. But you have it automatically with just one. You got the other because we cleared the air with that originally. And then the other two are exactly the same thing, except you really need that you're working with the only certain assignments. Yeah. The assignments that are convenient. I mean, you got to use double max. Yeah. So that these are in fact indiscernibles, technical points. Yeah. And now we have finished section 4.3, and we're exactly at the point where in section 4.4, the last lecture, we started with these 3 statements. So the link is very tight between the 2 sections. Andreas, I'm done, or I have 30 more, maybe 10 more seconds, but I'm done.